Yeah, so I'm going to be talking about what he said I'll be talking about. I am a statistics engineer at EPO, which is basically half data scientist, kind of half engineer. So I'm implementing statistical things frequently for our experimentation platform. And so you'll be hearing a bit about our platform and what it does, but that's not really the focus here. This is the ML applications track, so this is going to be about kind of half of the application of why we want to predict things in an experimentation context, which is might not be immediately obvious, and then kind of half engineering and really focusing on the algorithms and implementation. So that's what you can look forward to. To kind of motivate this, I'm going to talk about the #1 problem in experimentation. But before I get to that, I just want to step back a little bit and just really describe what an experiment process looks like at a company or even in the academic or scientific world. So the first thing that happens when an experiment runs, or just at a very high level, is you'll have a lot of users and you want to randomize them into at least 2 groups. Typically you have a treatment and a control. In this little diagram, I've got users coming in with different IDs, and then I need to assign them randomly to one of 2 treatments. In this case, this might be like a marketing promotion. I'll show half of users save 75%, and then I might show the other half like this yellow sale button over there. But the overall pattern or the overall flow of an experiment looks something like this. You start out with a planning phase, and this is going to be one of the focuses of the talk today. But you need to determine the number of users who will go into the experiment before you even start the experiment. And this is something that's often overlooked and can lead to some trouble if you don't pay attention to it. The second phase in an experiment is the randomization, sort of that black box that I showed you in the last slide. You need some algorithm to randomly assign treatment control or to multiple treatments. And then you need to wait and collect data on your users. So you're going to be measuring something. You're going to need some fixed time period over which to collect data. Could be a revenue metric, just could be any user level metric that's going to be of interest to the business. And then finally, after you've waited, after you've collected the number of samples that you determined during the planning phase, you'll analyze that data. And so you'll compute metrics, run statistics, get some p-values, get some confidence intervals, and hopefully make some kind of business decision to decide whether or not your treatment is a good idea for your business. I want to talk a little bit about statistical power, and this is something that people who kind of go through those 4 steps might not necessarily understand. I guess kind of just get a quick show of hands of people who have heard of statistical power. Okay, maybe about half. Sometimes people have a hard time wrapping their minds around it even after taking a Stat 101 class. There are basically 2 types of lifts that we need to think about. And so a lift here is just what's the % increase in a metric of interest. We have what's called the true lift, which is if we were to gather an infinite amount of data, observe an infinite number of users, what would the observed lift actually be? It'd be, could be 10.12489%. But we don't have an infinite amount of data. We only have, a finite user population. So instead, all we have to work with is the observed lift, which is not going to be the same as the true one. And so power deals with the relationship between that true lift and the observed lift. And so it's defined in relation to something called a minimum detectable effect. The idea is if the true lift is equal to some number known as this minimum detectable effect, what % of the time will an experiment give us a statistically significant result? And it's just a concept I find myself repeating quite a bit in the experimentation world, because if you don't have enough power for your experiment, your results will look something like this on the right, which is you have wide confidence intervals, all your results are statistically significant, and you don't really understand why. And the reason is you just didn't have enough users enrolled in your experiment in order to have, to see anything useful in the data. So power is just a recurring theme in the world of experimentation. And yeah, it makes PMs sad when they don't get stat sig results. How do you compute power? There are sample size calculators out there. This is one I just screenshotted from my website. It's just a little JavaScript calculator. It has kind of the core concepts here. So if you have some process with a conversion rate that you kind of know in advance, let's say a checkout rate of say 2%, you would define a minimum detectable effect in relation to that. So you say, all right, I want to be able to detect a change of at least a relative change of 10%, some percent of the time, and that would be that percent of the time is known as the power. How many users would I need to enroll in this experiment? And so with those two numbers, you want to be able to detect a lift from 2% to 2.2%. You need about 78,000 users in each treatment of your experiment, which might sound fine and great. 10% is a pretty large lift to be detecting for most like product feature changes. And so you start to really run into trouble when you dial that down and want to detect smaller and smaller effects, which you would want to do if you're just trying to test every single change that you might make to your website or your product. So just to show you a different set of numbers, and this is where people's minds start exploding, is if you want to detect a 1% change instead of a 10% change, you need about 7.5 million users enrolled in each branch of that experiment. And you know, this is just going from that 2% number to like a 2.02% number. And you know, if you're Facebook or another very large company, 7 million is nothing to you. You've got all the users that you need for very precise experiments. If you're everybody else, that number can look pretty intimidating. And so a recurring theme in experimentation is knowing when not to run an experiment because you just don't have the users for it. So is there anything we can do to reduce this number of users that we need for a successful experiment? And it turns out that there is. So I'm going to be talking to you about Cupid, which is a paper from 2013. This was a method invented by some researchers at Microsoft. Some of these names might be familiar: Alex Ding, Yazoo, Ronnie Kohabi, and Toby Walker. And it essentially reduces the number of users that you need in an experiment. I say with magic, it really just math. And it's a technique called variance reduction. And so I'm going to kind of walk through the mechanics of how Cupid works and then show how we implemented it at EPO. And the core idea here is that we're going to be looking at how the user's behavior compares to their predicted behavior and kind of take the difference between those two things in order to have a more, get a measurement with less variance than before. Okay, so how does it work? This is the kind of same illustration as before, but instead of just assigning each user to treatment or control, we're going to attach some additional data at that time of assignment. So at the assignment time, the user has not been affected at all by the experiment, and so we're kind of free to supplement that variant information with other information that we have about the user and construct just like a data set with that. So in this case, I'm going to attach previous revenue figures from those specific users. So I might know that user ID 12 had $120 worth of revenue in the past month, and 43 had $30, and 67 had $328. And I'm going to use that information in order to run a more precise experiment. I'm going to show you how that works. So this is just a very simple data table that we can construct with the user ID, the variant, this predicted revenue. In this case, I have the world's simplest predictive model, which is that their last 30 days is going to be equal to their next 30 days. We're going to get into more advanced models, but this is just for purposes of illustration. And then instead of analyzing the actual revenue that we get from each user, which is that fourth column, we're going to be analyzing the last column, which is the difference between the actual observed revenue and the prediction. And this is all these are just made up numbers, but the key insight here is that the variance in that last column is significantly lower than the variance in the next to last column. And so this is just the core idea behind Cupid, is that we just have much tighter numbers just looking at those residuals compared to prediction rather than just the observed values. So, and viewed another way, this is just an illustration I put together for one of our blog posts about this. But without Cupid, you might have two different estimates of some metric of interest. This will be the ones on the left. You might have a control and treatment where the uncertainty is relatively wide for both of those numbers. And then once you apply Cupid, because you have less variance in your data, you have much tighter estimates on what the mean is for each group. And so with that, your p-values are lower, your confidence intervals are tighter, and everybody goes home happy. Okay, so just another sort of illustrative diagram here. With Cupid enabled, this just means that whereas your sample size calculator may have told you needed like 120,000 users before, if you flip this on and you provide some of this pre-experiment data and reduce the variance, kind of typical results here are you could get that down to like 50 or 80,000 users. Sometimes it's more than that, sometimes it's less. This is just kind of a rough ballpark of kind of typical results that we've seen and that other organizations have reported. So none of this is new. This is all stuff originating from that original Microsoft paper, pretty widely used in the industry. Okay, so how do we implement this? It all sounds great. We get experiments that require fewer users than they did before. Let's go to work. So this was the first version of our Cupid architecture. You kind of read it from bottom to top here. So in our system, customers have all their data sitting in a data warehouse. We have Snowflake, BigQuery, Redshift, and Databricks represented. And so the customers will have just event level data there. And we crunch a lot of numbers, compute subject level data out of that for each experiment. And then we're going to want to run some kind of computation on that subject level data. So I've labeled these kind of big data at the bottom, which is just event level data. Medium data in the middle row just refers to subject level data. And then finally, once this Python process is done, which is using these technologies, SciPy, NumPy, and Pandas, we get tiny data, which is just the actual confidence intervals for the experiment results. So that will literally just be like 5 rows going into our Postgres table at the end. So what's this middle row doing? It's a pretty kind of standard data science-y architecture. We got a Python process that runs. It connects directly to Snowflake. It downloads a big table. It pivots in memory in a way that Pandas is going to be happy with, that we can run linear regressions on. And then finally, we run those regressions using NumPy. So this is nothing too special here. Pretty easy for data scientists to write and get it stood up and go to work. So this is just a little bit of this is an actual screenshot. Don't tell my boss, but this is a fairly, you can just see kind of how simple that fit and predict method ends up being, just using Python, using Pandas. It's all kind of at the bottom. We get an estimator, we fit it, we make some predictions using that estimator, and we return those predictions and then do all the stats kind of on that array of predicted values, or the difference between the prediction and the residual, depending on kind of which exact version of Cupid that you're doing. But it's nice, clean code, and that's just all I kind of wanted to show you in this slide. So yeah, we rolled it out. It worked well. So I just kind of took this example at random. We've got a little checkbox on each experiment result page. You can turn Cupid on or off. And this one's more or less taken at random. The confidence intervals are just slightly smaller, but sometimes that can kick a statistically insignificant result into a significant one. And that makes people happy when they have those tighter confidence intervals. One thing worth noting here, it's not really important, but the point estimates from Cupid results are different from non-Cupid results. and that just makes people's heads hurt sometimes. So they're both consistent estimators of the same thing. The actual measured difference that you see, or like the observed lift, is not the true lift in the first place. And likewise, with Cupid applied, the sort of predicted lift or the estimated lift is also not equal to the true lift, but it's a consistent estimator of that. So just some little wrinkle that you might have to describe to Cupid users. Okay, so that was all well and good. People were happy. Big hooray until the scary ellipses. Start seeing things like this, which most developers have seen at some point in their life in some way, shape, or form. And in our case, it was the node was low on resource memory. Some container was trying to use a ridiculous amount of memory, which exceeded the request size. And so it's evicted, and the process or Kubernetes pod is killed without ceremony. So this is an actual Slack message I got from one of my coworkers one morning after some of a Cupid process was running on one of our larger customers. He just said, "Whoa," pasted in this graphic of memory consumption and what caused big spiky. And this became a recurring pain point, is memory. So in-memory analytics all sounds well and good, but there ends up being a lot of operational issues in terms of provisioning machines with the amount of memory that you need, knowing in advance how much memory you will need before you provision that machine, paying for it, like keeping data in memory. Kind of the second point is about 500 times more expensive than keeping it on disk. And then finally, getting data from your warehouse into memory can take a long time. So if you look at this graph, this is actually just our Python process trying to download data from Snowflake for 3 hours and slowly growing its own memory usage. And then finally, at the end of, I guess, 3.5 hours, it has everything in memory and then tries to pivot it. And that's where this big spiky comes in and kills the process. So we just started to hit some pain. We did an investigation into our Python process and our Cupid jobs. It's just a screenshot from this internal investigation that we did. And about half the jobs failed. Some would take 13 hours and succeed. Others would take 3 hours and run out of memory. And a lot of this time, kind of in the last column you see there, was just from fetching and pivoting data. Really just downloading data from the warehouse and then trying to get it into a form that pandas could use. And so this is my life for a few weeks, just trying to debug these issues. And so maybe it looks familiar to some of you out there. Okay, so how do we get around this? We kind of took the Python process to the limit of what we could do with that architecture, and then we started casting about just for some other ideas to get around the memory issues in particular. Two options that we considered are described here. The first is use a warehouse-specific machine learning solution. Redshift has SageMaker, BigQuery has BigQuery ML. I'm not sure if Snowflake has anything yet, and then Databricks is hooked up to Spark. For our use case, we needed to support all 4 warehouses. Like some of our customers are on each warehouse. So they would have been costs associated with using developing against a specific warehouse, whereas the rest of our code base might have only 100 or 200 lines of warehouse-specific code. The advantage of this approach is that you don't have to move the data out of the warehouse, or at least from the customer's perspective, it doesn't look like you're moving it out. There's still kind of physical data movement happening from BigQuery's table system to their ML system, which does have time and costs associated with it. But from the customer perspective, they just think it's all sitting there. But the drawback, there are those extra costs associated with moving that around and using kind of these fancy ML systems. And there are also extra permissions required for some of this. So we got in kind of an awkward situation where we're trying to ask customers to grant us more permissions on their warehouse account and trying to explain why we needed it compared to just the read-only BigQuery account that we had. So there are some real drawbacks to that approach. Another option would have been using Apache Spark or Databricks and just moving all that data out to a scalable system that knows how to do linear regression and has kind of solved this problem of trying to run regressions on large data sets. That would have been nice because it would work across warehouses. The downside, of course, is that we have to move data out. We do have a lot of customers who are in kind of constrained regulatory environments or are sensitive about PII leaving their systems. And so they weren't too keen on us downloading data either into a Python process or into a Spark process. So we considered those, and then we thought about what if there's another way here? So this is a quote. I first came across this. It's like in the essays of Francis Bacon. I think it's kind of famous at this point. There's a story in, I don't know if it's apocryphal or in the Quran, but Muhammad is with a number of his followers, and at some point commands this mountain to move to him. And of course, the mountain doesn't go anywhere. And so he kind of smiles and says, well, if the mountain won't come to Muhammad, then Muhammad must go to the mountain. And I like this because if the data won't come to you or to come to your computation, maybe you should bring your computation to the data. And so that will be the theme of the rest of this talk. All right, so what are we actually trying to do? Our specific predictive model was just a linear regression. It wasn't the super simple one that I showed you, but essentially we are trying to predict the value of each metric using all metrics for a specific user. So the basic linear regression equation, if you remember from a stat class or econometrics class, I'm trying to solve x beta equals y. You're solving for beta. Y are your covariates or your inputs. These dependent variables, so these would be previous values of metrics. So we'd have one row per user, one column per metric value. And then we want to predict each user's value for a single metric, and that's going to be our y column. And then beta is just our kind of best fit coefficient vector. So nothing too crazy here that we're doing. The solution to this equation is this very famous equation, the beta hat, or the estimated beta, x prime x inverse, x prime y. And so I really want to just look at this equation and figure out if we really needed Python or anything too fancy to compute this thing. And so our core insight was this, that this x prime x matrix is a k by k matrix. So if k is the number of columns or metrics, then the result of this product is not a gigantic matrix with like a million rows or a million columns. This is a very small matrix. So if we have 10 metrics that we're interested in, the x prime x matrix will be a 10 by 10 matrix. And it turns out each cell is very simple to compute in SQL. If we have a constant term, then the top left term will just be a count of the number of rows. We all know how to do that in SQL. This top row and first column here, again, if there's a constant term, it's just going to be the sum of each column. And then each one in the middle is a sum of an x times another x. And so this is very easily expressed as a select. And it turns out that these warehouses are highly optimized for these kinds of problems of multiplication and addition. So similarly, the other half of that equation, x prime y, is also very simple. The first term is just going to be the sum of y's, and then the other terms will be sums of various x's times y's. So what does that mean we can do? If we can compute those two terms in SQL, then we can solve the rest of the equation kind of in the control plane or at the application level. So this is, just a little screenshot from our new code base. But what this is doing is after we've computed the x prime x and x prime y using SQL, then we can just invert it, which is the second line of code, multiply the x prime x inverse by x prime y, which is the third line of code, and then get a variance covariance matrix out of the end with the fourth line of code. And you don't need Python for this. Any library or any language that has a matrix library and a kind of a set of special functions, if you want to get p-values and things, is sufficient. So we ended up being able to do this using TypeScript for our control plane. So what's the new architecture look like? It's something like this. So we've got that big data still sitting in the warehouse, but now we just do a lot of extra compute in that warehouse. So we do all those sums of x times y's in the warehouse, and then only, instead of downloading the subject level data to our systems, we just download that x prime x matrix and the x prime y matrix to our system, do the matrix inversion, the multiplication, get the variance covariance matrix. And this is all I've labeled small data since it's just those k by k matrices, and then get the same kind of tiny data or results out the other end, which is just the actual experiment results kind of being written to our production database. How'd it work in practice? We saw some pretty big speed ups. So I just picked a couple of specific experiments that had been around kind of before our architecture change and after. We had one go from 9 hours down to, I think, 45 minutes. Another one go from 9 minutes down to under a minute. This really just speaks to how long it takes to download data out of a warehouse, and also just how well these warehouses do with sums and multiplications. We have some fairly complex models. I think the most complicated is like a 300 by 300 matrix, but these BigQuery just tears through them. It does all the parallelization, both the column level and row level for us. It's really good. They're really good at what they do, and we're able to leverage that in our new system. So yeah, so what are the benefits of this architecture? This system works across warehouses pretty well. So it works on all 4 warehouses. As I said earlier, our warehouse-specific code is just 100 or 200 lines of code per warehouse. So if we want to add another one, an engineer could do it in a few days. We use existing application language and infrastructure, and this has been a really big gain for us. Prior to this change, we had sort of like a little Python universe and a TypeScript universe, and it was just hard to move engineers between those two code bases. We had all kinds of duplication just trying to communicate our data model from the TypeScript land over into the Python land. So it could just be just simple things like describing what are the experiments, what are the variants, what are the treatments, how do we get that over from our main application into this external system? Do we need a microservice around it? All those problems go away once we're kind of on a unified language and able just to reuse frameworks, both for statistical and regular application code. We don't move data out of the warehouse. This is very good for customers who value that privacy. We can assure them that we never see user level data. Makes the SOC 2 people happy and everybody a lot happier when we don't actually see their users. And then, as you saw in the graphs, you get much faster results out of this thing. The architecture is a lot simpler. We're just able to rip out a lot of code, which always makes me happy. And then finally, we don't see a lot of out-of-memory errors anymore. Previously, we just kept doubling the amount of memory that we try to provision for these Python nodes, starting from 20 gigabytes, 40, 80. I think we topped out at 160 before we moved on to this architecture. And as we were running the math, we weren't making much money off of our contracts with customers just because it was all going into these high memory machines that are really not that cheap on these cloud systems. And now I think the biggest node we have is 2 gigabytes. But it's not all sunshine and roses, just a few pitfalls that we ran into along the way. Some of these queries do get very large. I was actually able to hit the 1 megabyte select query limit in Snowflake, just with the sheer number of sums that we were doing for some of these large models. And also found out that Redshift has a column limit of 1,600 in their result sets. So you got to break up some of these queries into multiple queries. It doesn't have a huge effect on throughput because the second point is you can parallelize just by querying concurrently. Warehouses are very good at just taking multiple concurrent queries and then doing their own parallelization within each query. It helps to have a language that lets you do concurrent querying like promise.all, which we use in our Node.js. You can still hit OOMs. I think we've hit a few just because in JavaScript, it's not like this super dense matrix representation. They're like boxed primitives and arrays and things. Not a huge deal, but just something to be aware of if it's not like just this tight array or a tight matrix of floating point numbers. And then another little gotcha that I hit, the second to last point is the literal 1.0 doesn't mean the same thing across warehouses. Like, there's no such thing as standard SQL. Some warehouses, that's a floating point number. Other warehouses, that's a fixed precision decimal number. If you're not really paying attention to this stuff, you'll just get these weird overflows or errors where it's trying to mix fixed precision and floating point precision arithmetic. So just make sure everything's float and your life will be a lot easier. And then the last little gotcha, this is sort of an advanced point, but we tried implementing like heteroscedasticity robust standard errors, and that got a little bit trickier because we couldn't use the same trick of like reusing this x prime x matrix. I don't really want to get into it, but it would have ended up being a lot more computation than we signed up for. But for plain OLS problems where you have the same equation structure or the same specification on the right-hand side, you can reuse that x prime x, which will make everybody happy. All right, future directions. Where can we take this thing? I spent time over Christmas just trying to get quantile regression working on these warehouses. It's a really neat paper from Roger Kinker about this, what he calls the Frisch-Newton method. It happens to map really well to kind of just like the warehouse architecture or SQL tables. I had fun doing it. It's an iterative method. It seemed to work pretty well. We haven't done it in production or anything, but it was a neat little proof of concept that you can do other kind of nonlinear regressions if you'd like. And so the way that works, instead of minimizing the square of the errors, it'll minimize like an absolute value of the error. Ridge regression, that's just another variant of OLS. You just add like a k times I term across the matrices. Pretty easy to add. That's what we do in our production code. So that works as well. I'm pretty sure a lot of different generalized linear models could work here. Kind of in my previous job, I implemented a lot of these by hand in a non-server context, like Probit, logistic regression, Poisson regression, all your favorite GLM models. I'm fairly confident could be done, but with one caveat I'll point out on the next slide. Or your algorithm here. I'm pretty excited just kind of at the results that we were able to get, just going back to those core equations and scratching our head a bit and seeing if we could implement these in warehouses. A lot of these algorithms are really just dot products. They are just sum of x times y. Like large language models kind of fall in this category, although I'm not going to tell anybody to try to do that. Warehouses are just hyper optimized for multiplying and adding. It's what they do well. Let them do what they're good at. The one caveat here is for certain types of models, you might want a special function that's going to operate at the row level, like a log gamma function, digamma, kind of all these special functions you might see in a statistics textbook that might not be available natively in a SQL environment. For those things, you might need to implement that as a UDF. Warehouses have all kinds of UDF solutions, either with Python or JavaScript, or just kind of implementing a polynomial approximation yourself. So that might be necessary if you're going to do something like a Probit regression. So, kind of wrapping up, why would you consider this architecture? Portability. If you are just trying to do ML across warehouses, SQL, there's nothing more portable than SQL. I put worse is better in quotation marks here. This is a reference to a famous essay about Unix arguing that Unix became popular in the 70s because it was worse than the alternatives. It was easier to implement because it had fewer features. If you can do things in SQL, you can kind of do them anywhere. If your warehouse-specific ML bills are getting out of control, this would also be another reason to consider this. I think there's just a lot of unnecessary overhead with those systems, both moving the data over to them and the type of compute that's done on them. Data movement, taking too long. If it's being too annoying, think about this. If your ML stack feels fragile, if you're hitting all those OOMs as frequently as we were, warehouses are very robust. There are certain types of operations where you start to hit their limits if you're doing trying to do 50 subselects or do all these percentile calculations. But for sums and multiplications, you're not going to break the warehouse, but you might break your Python process. And then finally, of course, you're just bored and want to try something new. I'll be happy to tell you more. So that's all I have. Thanks for listening.
Yeah, this is a very interesting talk. I am fascinated by the continual use of SQL databases for things that I didn't expect. My question for you is how many covariates? Because it seemed like the crux of the solution is that the number of covariates is not too large, right?
Yep.
Because the problem it seemed like we were having was you were bringing in too much data, and but if you think about things in terms of covariates, then it stays small. How long is that true for? Like, how many covariates do you have to add before you have to start thinking of another approach?
Yeah, that's a good question. Our architecture currently, we deal with about, I don't know, kind of tens of millions of subjects or rows, and up to maybe 300 covariates, I think, is our largest model. If you saw the specific limitations, there was the Snowflake 1 megabyte query limit kicks in. We've hit that with those 300. Then there's the Redshift 1600 column limit. So if you think of a 300 by 300 matrix, it's going to be whatever 90,000 entries in that matrix. You're going to have I don't know what 70 separate queries just to get Redshift to process through all of those. So I think if you start going much beyond that, you'll just have to kind of break it up into more and more queries. I think, it's an engineering problem. Those are sort of the constraints around that. I'm not going to put a hard and fast rule, but I think if you get up to if your application environment does not have a good, dense matrix representation, then you're also going to hit trouble if you have if you're 10,000 by 10,000 or something and trying to represent 100 million objects like boxed numbers. You're not going to be in for a good time. I'm sure people could take it further than we have, but that's the way that I would think about trying to scale the system up.
Thanks.
Great. So you mentioned you did some query partitioning. So you generated multiple queries to be able to tackle this problem.
Yeah.
The speed up that you showed between the 9.5 hours, 45 minutes, was there parallelization on the query side?
Yeah. There's yes, a lot of parallelization on the query side. So
that even though the time is shorter, because in these systems like Snowflake, the query time translates to cost.
Yeah.
For single queries, and then you parallelize. How is the cost side of this?
Yeah, so it does move cost into the warehouse. What we've seen is it's not the big cost center yet compared to computing on summing over the number of events and facts and condensing that into subject level data. I'd say it's about kind of 50-50 between the Cupid part of things and the everything else part of things. It also it depends on the kind of the warehouse billing model. So for Snowflake in particular, time equals cost. they bill you for the number of minutes that your Snowflake cluster is running. And so yeah, that's a nice one-to-one kind of cost model. But yeah, so especially since the compute grows is like k squared. As you add tons of covariates, that's going to add a computation quadratically. So yeah, that's something to be aware of.
And the subject you mentioned, like hundreds of millions. This is after applying Qubit to reduce the number of subjects you would need to draw a conclusion.
Right. So it kind of depends on whether the customer decides to use the variance reduction to reduce the number of subjects in the experiment, or just to get more precise estimates out using the same number. So we can't tell them to use fewer subjects. Yeah, but it could take that number down 50% or so.